As I promised everybody, I would make a recording of part of the chapter 20 slides, but I felt bad because I really want you to do well, and so I decided to go through all of them, so I recorded the entire chapter. So let's go ahead and begin. We're going to start with slide 1, where basically we're talking to you about what electrochemistry is. This field deals with how chemical reactions produce electrical energy and how electricity can be used to drive chemical changes, like a motor or your cell phone or whatever. You've already seen this in real life anytime you've used a battery or watched metal rust. The first slide here reminds us that moving electrons in batteries can create electronic current. These currents can power anything from LEDs to electric cars. What's more exciting is that some batteries can be recharged using solar energy, which is one of the ways we can start to imagine living off the grid. As you all know, people in Nevada take advantage of that. So this chapter isn't just theoretical. Electrochemistry is absolutely essential in a real-world energy system. Electricity in our modern context is a fundamental form of energy. It powers homes, factories, smartphones, cities, but underneath it all, it's just the flow of electrons from one chemical species generally to another. So how exactly do we get from chemistry electricity? That's what this chapter will unpack, starting with the basics redox reactions. When we talk about redox, let's start with the foundation of electrochemistry, which is oxidation reduction. There are chemical processes where electrons are transferred between atoms or ions. In a redox reaction, oxidation is the loss of electrons, as I went over in class. Reduction is the gain of electrons. A good way to remember it, since I'm from Texas, is oil rig. Oxidation is loss, reduction is gain. Take sodium and chlorine for example. Sodium is oxidizing because it's losing an electron. You indicate that by showing the electron on the product side. Chlorine is under a reduction. We indicate that to the reader by showing the electron on the reactant side. This kind of change in oxidation state is how we identify a redox process is happening. We can follow the electron flow just by keeping track of how these oxidation numbers change from reactant to product. Half reactions. Now that we know what redox means, we can break it down further by writing what's called a half reaction. A half reaction is one part of the redox reaction, either the oxidation part or the reduction part. Here's how they work. In oxidation, half reaction electrons are products, showing that something is losing electrons, as we indicated earlier. In the reduction half reaction, electrons are reactants. This is showing something is gaining electrons. These half reactions are helping us isolate what is happening at each electrode in an electrochemical cell. This is why we have to show them. They're the basis for balancing redox equations and calculating voltages later in the chapter we go over. By balancing redox reactions, especially in solution, this can get actually pretty tricky or pretty difficult as we showed you in class. We use half reaction method to balance each part of the redox process separately. As the bullets are showing you, this is the general procedure. You're going to break the reaction into oxidation and reduction half reactions, balance each half reaction for mass and charge, and then combine the two and cancel anything that appears on both sides. This approach is essentially useful when working with reactions in water that are either acidic or basic, and I have to tell you that to help you solve the problem on the exams. It lets us keep track of atoms or electrons methodically. In more detail, though, if we want to walk through this, you would assign oxidation states step 1 according to the textbook, write the oxidation and reduction half reactions, then balance each half reaction for mass because we cannot create or destroy mass, so we have to balance it. First, balance all elements except H and O, then balance O atoms by adding water, and then balance H atoms by adding H+. If the reaction is in a basic solution, you would then neutralize the H pluses with OH to convert it to water and have excess OH on one side of the equation generally. Then balance the charge by adding electrons, make the number of electrons equal in both half reactions by multiplying with whole numbers as needed, and lastly, add half reactions and cancel anything that appears on both sides. After you're done, double check the total number of atoms and charges that are balanced on both sides of the equation. And as I said in class, if your hydrogens are balanced, most likely everything else is balanced. So what's the new stuff? Well, I was hinting at this in class, but let's continue on in a further discussion. When electrons flow through a conductor, such as a metal wire, they generate electrical current. This is similar to water flowing through a pipe due to the pressure difference, or downhill through the gravitational difference, except in this case it's electric potential. Current is simply the amount of charge that flows past a point in a circuit per unit time. We measure it in amperes, where 1 ampere, A, is equal to 1 coulomb flowing each second. And as you see here, 1 ampere is equal to 6.242 times 10 to the 18th electrons per second. This applies whether charges are electrons flowing through a metal wire or ions flowing through an aqueous solution. It's all about the motion of charge. The key idea is that chemical reactions can create the electron flow if we separate the oxidation and reduction processes so that electrons are forced to travel through a wire, we get usable electricity. What you see in this slide, though, is a visual reinforcement of that idea that electrons move through matter when a potential difference is present. As you see here, the zinc strip is getting copper deposited on it due to the flow of electron current. When the atoms in a solid conductor are connected to a source electric potential, the electrons are actually jumping from one atom to the next, flowing through the material. In metals, electrons are delocalized. If you recall, if you had me for Chem 1, I told you that metals basically are seas of electrons, like the ocean sea, not the letter C. And they're free to move throughout the lattice, which makes conduction possible and why metals are used typically in building electrical systems. This is a microscopic view of the electrical current, where electrons are hopping from atom to atom through conductive material. Now, this potential difference, or the driving force behind electron movement, is known as potential difference, which is measured in volts. It is representative of the difference in potential energy per unit charge between 2 points in a circle, or excuse me, in a circuit, not a circle, in a circuit. So 1 volt equals 1 joule per coulomb of charge, basically. That means that 1 volt will push 1 coulomb of charge with 1 joule of energy in electrochemical systems. We often refer to this as EMF, or electromotive force, even though it's not actually a force in the physics sense or the classical sense. Think of it as a push that moves electrons through a circuit from the anode to the cathode. Cell potential is the total voltage produced by a redox reaction when it occurs in an electrochemical cell. It's also referred to as E0 cell because it's under standard conditions typically. This potential is the difference in electrical potential between two electrodes. And later on you'll see me show you the math where the difference between the cathode and the anode is that cell potential. A positive cell potential means the redox reaction is spontaneous. That's important. This is what we want in a battery or a voltaic cell. We want it to be spontaneous, so the minute you put it into a device and you turn it on, it provides current. Understand standard conditions is 25 degrees Celsius at 1 atm for gases, 1 molar ion concentrations, so that you know. In an electrochemical cell, okay, and we can skip this slide here. We'll just get to electrochemical cell. So what this is basically showing you here, let me back it up because I don't want to not cover it. What this is basically showing you here is that the reason why this is spontaneous is that this potential is great enough that electric flow can occur. And you're going to see systems where this happens. And quite readily in systems where it doesn't, especially in lab when you have lab next week. An electrochemical cell works by separating the oxidation and reduction half reactions into different compartments called half cells. Each half cell contains an electrode and an electrolyte. The anode is where the oxidation occurs or where the electrons are lost. The cathode is where the reduction occurs or the electrons are gained. Electrons flow from the anode to the cathode through an external wire, while ions move through the salt bridge or porous barrier to maintain electrical neutrality. This setup allows us to capture the energy released by a spontaneous redox reaction and convert it into electrical work. In an electrochemical cell, each half reaction takes place at an electrode. So this slide is breaking that down further. The anode is where the oxidation occurs. It's the source of electrons and is negatively charged in a voltaic cell. Keyword, voltaic. The cathode is where reduction occurs. It receives electrons in a positively charged voltaic cell. A salt bridge is a U-shaped tube filled with a strong electrolyte connecting the two half cells. It completes the circuit by allowing ions to move in between compartments, balancing the charge electrons flow through the wire. This is something that you will get to see in lab. Without a salt bridge, the charge would build up on each half cell and stop the reaction. The salt bridge ensures that the flow of electrons can continue. For electrodes, the material we use for electrodes depends on the redox reaction. If a metal is oxidized, we use that same metal as the anode. If a metal ion is being reduced, we often use the corresponding metal as the cathode. But not all reactions involve solid metals. If the species being oxidized or reduced is a gas, or if it's all in solution, we use an inert electrode, typically graphite or carbon or platinum, that do not participate in the reaction but provide a surface for the electron transfer to occur. A voltaic cell is an electrochemical cell in which spontaneous redox reactions generate energy. What are some of the key points you need to know? The anode is the source of electron and it's where the oxidation occurs. The cathode is where the electrons flow to, so the flow is moving in this direction, from left to right or anode to cathode here, and it's where the reduction occurs. The electrons move through an external circuit and then it passes as ions through the salt bridge to complete that circuit. We will learn how to represent these cells using cell notation, which is covered in the next slide. So when you cell note, it's basically a shorthand way of describing the setup of an electrochemical cell. The format is simply the electrode and the solution with a double line where the solution and the electrode. So what do these lines mean? The single line represents the boundary or the phase barrier, okay? The double line typically represents the salt bridge in our voltaic cell. So the best way to explain this would be to just show you an example of this. So let's go ahead and show you. So in this particular notation, what are we showing you? We're showing you that iron, right? Iron metal is in a solution of iron where the salt bridge present, and then on the cathode side we have a permanganate that's with manganese, hydrogen, and then a platinum solid, because in this case we need something to just help electron flow occur. So that's basically what's happening. Okay, you could say that this is an inert reaction where predominantly only ions or gases are moving in this sense as we were using platinum. Now, why is this important? Well, there's a little math involved. In electrochemistry, we can't measure the absolute potential of a half cell by itself. We can only measure it relative to another half cell. To solve this, we use what's called the standard hydrogen electrode, or SHE, as a reference, assigning it a potential of exactly 0 volts. What a standard hydrogen electrode is basically 2 protons plus 2 electrons coming together to form hydrogen gas. And that's what we're telling you here in the slide. Every other half reaction that we're going to show you is measured relative to this standard. The more positive a reduction potential, the greater the tendency to gain electrons or to be reduced. The more negative the potential, the greater the tendency to lose electrons or to be oxidized. So the question we need to ask is, which way will the electrons flow? Electrons flow from the half cell with the lower reduction potential to the one with the higher reduction potential. So as in the example you see, zinc has a standard reduction potential of negative 0.76. Okay. Cu has a standard reduction potential of 0.34. Now notice I said reduction potentials. Okay. The way that these are written to you on the slide are in oxidation potentials. Okay. And so in a zinc copper cell, electrons will flow from the zinc to the copper because zinc is more easily oxidized than copper. And the reason why we flipped it from what I read on to you earlier in terms of the values is because we want to show you the greater oxidation potential is the one that's going to be easier to oxidize, basically. So 0.76 is easier to oxidize than negative 0.34. All right. So we use a voltmeter to measure the potential difference between the two half cells in a connected circuit. These measurements are typically made under standard conditions. Again, to reiterate, 25 degrees Celsius, 1 atm pressure, 1 mole of concentration of ions. These conditions allow for us to compare standard reduction potentials across different systems using standardized values found in tables like 20.1 of the Brown and LeMay textbook. A half reaction, or in this case half cell potentials, a half reaction with a positive standard reduction potential is more likely to gain electrons as it has a stronger tendency to be reduced. Conversely, a half reaction with a negative standard reduction potential is more likely to lose electrons. It is a better reducing agent when reversed. You can combine the two half reactions to build an electrochemical cell. The one with the higher E naught acts as the cathode, and the lower E naught acts as the anode. Remember, you do not multiply the E naught values when balancing equations. These are what we call intensive properties, so it doesn't care about how much of it you have, which makes the math very easy. Okay? So you can predict whether a redox reaction is spontaneous using standard reduction potential table that you see here. Now, I joked in class and told you had to memorize every value. You really don't. You just need to know how to use the table because I would have to give you information if I asked you to calculate something. If the E standard of the cell is greater than 0, the reaction will be spontaneous. If the E standard of the cell is less than 0, the reaction is non-spontaneous. And substances at the top of the table are strong oxidizing agents, meaning they tend to get reduced, while those at the bottom, okay, which is on this table here, this chart here, will be strong reducing agents. They tend to get oxidized. Pairing a substance high on the table as a cathode with one low on the table as an anode is what gives us spontaneous reactions. And that is what we do when we build a battery. You're basically taking something that is a strong oxidizing agent and you're typically coupling it to something that is a strong reducing agent. So an example of this would be like a lead acid battery, right? If we were going to do a lead acid battery, we would typically use an acid of some kind at the top, like H2O2 going to H plus, something along those lines. It's not exact. Or like Pb plus 4H2E. And we would couple it to something down here on the bottom, like lead. And that difference would give you basically your spontaneous potential for the battery to occur or to do its things. To know whether a metal will, what is it? What was I say? So, in doing these reactions, right, when adding the E values, if you need to multiply half reactions to balance, you do not multiply it because they're intensive, like I told you. And the math is really simple. You simply take the E standard potential of the cathode and you subtract it from the anode. That's all you got to do. Now you got to be careful when you're doing these reactions because you got to make sure that you're looking at the half reduction potentials, because if you need the oxidation potentials, you need to flip the sign. So the sign should change. Okay? So, and I already went over that. Let's see. And I already went over that too. So here we are. So to know whether a metal will dissolve or not in terms of an acid, you will compare the E standard to the hydrogen electrode. Metals below hydrogen in the standard reduction potential table will dissolve in acids producing gas, H2 gas. Metals above H plus H2 do not dissolve in simple acids like HCl, but they may dissolve in what we call oxidizing acids like HNO3. And that is why in the electrochemistry lab, you're going to be asked to clean your electrodes using HNO3 because it's an oxidizing acid. It will help remove or dissolve things that won't readily dissolve. I didn't go over the math because I realized like the math is pretty straightforward. It's simply subtracting one number from another. So now when it comes to the math related to this in the Nernst equation or non-standard conditions, let's talk a little bit about this. So there's a direct connection between electrochemistry and thermodynamics, and that's why we often present them to you together and we often test you over them together. What you see here in this particular example is there's a relationship between K and G that I showed you back in chapter 19 that basically tells you that free energy is equal to negative RT ln K or KEQ. There's a relationship between free energy and the electrostandard or the standard electropotential of a cell, which is basically delta G naught is equal to N Fe delta cell. Okay, where F is Faraday's constant in this case. So because there's a relationship between delta G and K, and there's a relationship between delta G and E naught of the cell, then likelihood there'd be a relationship between equilibrium and E naught of the cell. So for a spontaneous reaction to occur, if E naught is positive and delta G is negative and the K is greater than 1, the reaction is spontaneous under standard conditions. In other words, you don't want to let your K be 0 because if it's at equilibrium, then there won't be a gradient enough to cause electron flow to occur. It's the general gist of what we're trying to tell you. Now, I'm not probably going to ask you anything mathematical relative to this, but you should kind of get an idea of what the relationship is from the triangle that I just read or went over with you on the slide. So real cells, and remember, everything we showed you earlier was assuming not, right, or standard conditions. But real cells don't always operate under standard conditions. We use the Nernst equation to calculate the E cell at other concentrations, right? And so the Nernst equation is shown down here at the bottom. What this is doing now is putting the relationship between K, the E naught of a cell, and essentially free energy. They're kind of all being relative to each other. This equation, what it's basically telling you is how the concentration affects the driving force for electron flow. If products build up and reactants are depleted, the voltage drops. When Q, or your reaction quotient, equals K, the cell is at equilibrium and the E is 0. In other words, there's no flow. You need to build up a potential to have electron flow. That's the general gist of it. You should be familiar with what the Nernst equation is as a definition. Oops. So, a concentration cell, which is what we're showing you here, is a special case of a voltaic cell. You often hear the term like Daniell cell, where electrodes of the same substance but the concentration of ions are different. Even though the redox couples are identical, the difference in concentration creates a potential difference. because now having greater concentration gives you a greater difference essentially. Electrons flow from the dilute side of the lower concentration anode to the concentrated side of the higher concentration cathode until the concentrations essentially equalize. The Nernst equation allows us to calculate this small but measurable change in voltage. Go into here. Electrolysis is the opposite of a voltaic cell. We use electricity to force a non-spontaneous reaction or chemical reaction to occur. This is done in an electrolytic cell, which requires an external power source. For example, we can decompose molten sodium chloride, let's say, into sodium solid and chlorine solid, running a current through it. Or by, let's say, splitting water, right? You've heard of electrolysis, splitting water. That's essentially what you're doing, right? And you see that on the slide here. This is how we refine metals. This is how we plate metals and how we split water, as I mentioned to you, into hydrogen and oxygen. Now, the differences between a voltaic versus an electrolytic cell is very important to consider for the exam. So a voltaic cell will convert chemical energy into electrical energy. That redox reaction is spontaneous. The anode is negative, and the cathode is positive. In an electrolytic cell, it uses electrical energy to drive a non-spontaneous reaction and requires an external power source where the anode is negative and the cathode is positive. Excuse me, where the anode is positive and the cathode is negative. See, I even made that mistake, but I caught myself. You have to be very deliberate when you're looking at this because it's real easy to switch those signs, right? Because the electrolytic cell needs electricity, okay, it's actually going to push electrons towards the cathode or the negative charge. That's why the sign flips effectively, okay? Whereas in the voltaic cell, it's a spontaneous reaction that's happening on its own, where the cathode is now positive and is effectively kind of pulling the electrons towards it. That's why you see your signs. That's how I keep my signs straight. And I had to catch myself, as you see, because it's very easy to confuse the two. So this difference in electrode sign is super important. Don't be like me just now and confuse the two. All right. And so to electrolyze a compound, it usually needs to be molten or liquid to allow ion mobility. Electrodes are often inserted, like I told you, like carbon or graphite or platinum. And during the electrolysis, the cations move to the cathode and get reduced. And the anions move to the anode and get oxidized. And that's pretty much what's happening in a electrolytic cell. So as I mentioned to you, there's not much math. The main math is basically, can you subtract? If you can subtract, then you'll be in good shape. I'm not going to ask you the math of a Nernst equation, but you should be able to define it. And I think I've covered everything in about 30 minutes. I don't want to make this video too long because I'm probably already boring many of you. So I wish you all the best. If you have questions, I do have office hours. Email me, reach out, however you need to. I hope this video was helpful in helping you prepare for the exam next week. When you come in the class next Tuesday, we'll have something to help you prepare for the test even better because I'll have had the test written and begin finalizing the study sheet for you all. Till next time.